last class we have discussed that about that magnetic moment, and after that today I will discuss nuclear reaction, because I came to know that that third unit is not started yet, na?
Yes, sir.
So that I want to discuss today. That's why I will go little fast. And if you could recall, we have already discussed about G factor of proton, neutron, and all. And whenever they will up or down, what will be that we know. Now we want to find the experimental value, right? Or we want to compare with experimental value. Then what we will do, from theory we should calculate expectation value of whatever you want to measure. Suppose expectation value of energy, that means that will be expectation value is always giving the value of your experimental data. Is it okay for everybody? किसी का भी एक्सपेक्टेशन वैल्यू ऑफ स्पीड, आप एक्सपेक्टेशन वैल्यू पढ़े हो, एक्सपेक्टेशन वैल्यू about expectation value of energy. You calculate expectation value of energy. Before that you need to write Hamiltonian, whatever, that is a separate issue. That means this expectation value will give you experimental result. हम लोग जो कैलकुलेट करते हैं, फाइंड द एक्सपेक्टेशन वैल्यू ऑफ ब्ला व्हाटएवर, तो उसका मतलब हम लोग एनर्जी कैलकुलेट करते हैं उसका, जैसे हाइड्रोजन हाइड्रोजन एटम का आप लोग कैलकुलेट किए हो, एक्सपेक्टेशन वैल्यू कैलकुलेशन किए, फिर दैट इज मैचिंग और व्हाट, दैट इज सेपरेट. एक्सपेक्टेशन वैल्यू मींस इट इज एक्सपेरिमेंटल वैल्यू. इज इट ओके?
Yes, sir.
So then whenever whatever we measured magnetic moment of some nucleus, in that case we should know it is correct or not. So theoretical things we will do. So that we have done, that means I will try now to calculate a expectation value of some nucleus magnetic moment, and what is happening, that we'll see. We found that I is equal to 1, it will satisfy. And for that, this is the magnetic moment operator. And we'll use this. And for A is equal to 1, that for neutron and for proton, both is off and off. This wave function I will use to calculate magnetic moment is experimentally observed. So you can write mu J. This is the experimental value, and the experimental value, that is expectation value of magnetic moment, that we will calculate. And we know this thing. And this is, we are calculating for L equal to 0, central potential, Newton problem. So in this case, this first term, this will get 0. Only this term will see. And where G spin for proton is 5.585691, and for G S for neutron, that is minus 3.826484. This value I will use. Now at the place of this wave function, this I will use this wave function to calculate expectation value of magnetic moment. So now I can write, this is gone, so I can write this is, and same here it will be at this place. I will write little Sn, and I can write this. So I want to split it. It will be like, make it bring out, and it will be CST mu n upon S cut SP plus SN mu n S cut. Similarly, is now when this spin operator will act to the spin of neutron. This is for neutron, and this is for proton, and this is for proton neutron. So whenever this spin operator of proton will add to the spin of proton, it will give h cut upon 2. So what will be this value? This value will be GSP mu n. Why this is mu1 when both sides have mu n upon h cut, and it will give you h cut upon 2, and this is that. Plus GSM mu n upon h cut upon 2, this is value we should have wave function. Then we will operate with this operator, then you will find what is the value of this. If you want to do this thing, then you can do it, no issue. So in this case, I will give you just hint, you will do that. For n equal to 2 and s equal to 1, you need to find what is the wave function that is you can calculate, and there should be a relation that m, or you can say capital I, should 1. And this is l equal to 2 means ml, because it is varying from ml to minus ml. So if you do this permutation combination, you will find whenever ml equal to 2, other should be minus 1. Otherwise, this additional will not give you I equal to 1. That means mi should be equal to 1, and mi should be ml plus ms, and if ml is equal to 2, ms should be minus 1. In that way, in the time, I am giving you this thing. So ms should be minus 1. And second, you will find ml is equal to 1, at that time ms equal to 0. Because both additions should be 1. And whenever ml equal to 0, at that time ms equal to 1. In this case, you will find this wave function, down, down. But this is the
सर एक और प्रोबेबिलिटी भी तो बन सकती है ना, ml इक्वल्स टू -1 एंड ms इक्वल
0.31, 0.1. And I will write this one here for n equal to 0. This value was 0.8795 new. And what is the observed value? You can observe value. Zero 0.8574 million. This we found. Now we'll see how much percentage is n equal to 0 and how much percentage is n equal to 2. So what we'll do for that? For that we'll write this wave function, that is the combination of a and b, where a is related to n equal to 0 and b is related to n equal to 2. From there, we'll calculate how much percentage of n equal to 0 and how much percentage of n equal to 2. So I can write this is n equal to 0 plus b n equal to 2. And there will be a condition, that is, you can write, that means I can write this is equal to a square A square, this value 0.8795 plus B square, that is this 0.3101 newton. Newton I'm writing, you will take it common, and this value should be this experimental value 0.857. mu1, mu n, all are gone. Then what is the other condition? That is A square plus B square is equal to 1. And the normalization. So from these two, you can calculate what is A and what is the percentage of A and what is the percentage of B. From there, you can find A is around 0.96, or you can find it is 96%, whereas B is 4. That means, what it indicates, that means the deuterium has not only a central potential, it has some part of non-central potential, that is A equal to. Now we'll see how it will physically be seen. There is a neutron and there is a proton. So we will discuss how to analyze this. How it will happen? It's like theta dependency. Sometimes it is not theta phi dependency. How it is physically possible? Well, you will see like suppose a particle, a neutron or a proton is like this. There is, of course, there is a good force interaction. Suppose I am standing here and Sarthak is standing there, and we are holding like this. There will be. And suppose I will get pain and Sarthak will get pain. So there will be some other force, like with some angle, like suppose this, somebody. And if my face is that side and somebody some other side and or some other angle, it will be like this. So there is a, of course, force variation, and which is giving it is theta phi variation, means angle. So in Newtonian case, we found that there is a no, it is like a only R dependency. But experimentally it is showing that as there is only one neutron and proton, there is some very small amount of maybe very small angle dependency, or L is equal to 2, their dependency. That is the what theoretical and experimental observation or our analysis is there. There is a small part of dependency of L is equal to 2 is inside the. Okay. This is about magnetic moment of deuterium. Now we'll go for the nuclear reaction. Am I audible? Hello? Am I audible?
Yes, sir.
Yes, sir.
Now we'll go for nuclear reactions. Actually, if we'll see in artificially, we can make the nuclear reactions. Like suppose it is like this way: x plus x, it is suppose giving this is capital Y and this is small y, and this is known as target nucleus, and this is projectile, this is, you can say, emitting or ejecting particle. Sorry, this is ejecting particle, and this is known as residual nuclei. So this nuclear reaction is represented by is it okay? That means nuclear reaction is represented by this, where this X is target nucleus, this small x is known as projectile. Projectile means suppose it is like this, you can see. Suppose this is suppose aluminum, copper, whatever. It is known as target, and some particle suppose is bombarded, it is known as projectile, and if it is something like some emission is occur or ejecting particle, it is known as ejecting particle. And suppose this remain nucleus is there, so it is known as residual nuclei. Is it okay? So nuclear reaction is represented by this presentation. Is it okay for everybody? No? Suppose we'll take some one suppose example. Like suppose alpha particle bombard to a aluminum, or you can say suppose boron. Okay, and it giving some suppose hydrogen, helium, it will give suppose helium and some particle. So that whatever which particle here, that means alpha particle is bombarding, and this is boron, this is target material. And after target material, suppose something, it is suppose example, suppose a neutron is coming out, so exiting or ejecting particle is neutron, and remain nucleus whatever after the ejection, it is, that means that will be the helium. So this is represented by this type of nuclear reaction. Is it okay? Am I audible? Hello, am I audible?
Yes,
हेलो,
sir.
ये सर जिस रेट में आप बोले इसका मतलब समझ में नहीं आया. Again I am telling. Nuclear reaction, artificial nuclear reaction, we can produce by bombarding of particles like oxygen ions or alpha particles, or you can say some photon incidenting of photons. So in this reaction, we can create ejecting particle or number different particles as well as different nuclei through this reaction. Is it okay? इसका मतलब हमने अल्फा पार्टिकल की, बीटा पार्टिकल की, ऑक्सीजन हेवी आयंस बॉम्बार्ड करके कोई भी टारगेट में, लाइक एल्युमिनियम हो, कॉपर हो, कि गोल्ड हो, इसके ऊपर बॉम्बार्ड करने के बाद इसमें से कुछ पार्टिकल्स भी निकलता है। नहीं तो कोई कोई मटेरियल में यूरेनियम में होगा तो वो फिशन होता है। दिस टाइप आर्टिफिशियल न्यूक्लियर रिएक्शन वी कैन अकर। ये समझ में आ गया? नहीं आया समझ में? Am I audible? नवीन, हेलो नवीन।
Yes, sir. Yes, sir.
तो ये समझ में आया नवीन?
Yes, sir. थोड़ा समझा.
थोड़ा समझ में आया मतलब that means what I am telling, through irradiations we can do nuclear reaction. Is it okay? Through irradiation means?
Yes.
Through irradiation means what? Means we'll give alpha particle or proton or neutron or oxygen atom or nitrogen atom. This is the bombarding particle. This particle will incident to a target, means कोई भी material होगा. Target means it can be uranium, it can be zinc, it can be aluminium. इसके ऊपर गिरने के बाद then what will happen? This high energetic particle, whenever they will collide, it will give a nuclear interaction and they will produce some alpha particle produce कर सकते हैं, नहीं तो अल्फा गामा प्रोड्यूस कर सकते हैं, नहीं तो एनपी रिएक्शन प्रोटॉन निकाल सकते हैं। जब भी न्यूट्रॉन गिरता है तो प्रोटॉन गिरता है तभी कुछ गामा निकल सकता है। इस टाइप का रिएक्शन होके पार्टिकल्स कुछ निकलता है। इस टाइप का रिएक्शन और कुछ जैसे उसके ऊपर गिरा, आफ्टर दैट देयर विल बी सम रेसिडुअल न्यूक्लियस, क्योंकि जब भी this emission particle will eject out, then remain nucleus will be something different thing or same thing that we'll discuss whenever we'll discuss about type of reaction. So that will happen. Is it okay? No? Okay. Am I audible? क्यों ये समझ में नहीं आ रहा है? Whenever a particle incident to a target material, it will eject some particle and remain, there will be a residual nuclei. Now we'll discuss. Somebody who will answer me? Atul? Atul? Atul, are you there? Nabin?
Yes, sir.
Why other people are gone?
Sir, I think network problem or something.
Are you am I audible to you?
Yes, sir.
अंजना,
Yes, sir.
सुनाई दे रहा है?
Yes, sir.
ओके. ब्रह्मानंद?
Yes, sir.
लेकिन आपको समझ में आ रहा है? ऑनेस्टली टेल मी. नहीं आ रहा है तो बोलो, डोंट वरी. ब्रह्मानंद?
Yes, sir. Yes, sir. आ
समझ
रहा
में
है.
आ रहा है समझ में? ब्रह्मानंद,
Yes, sir.
समझ में आ रहा है?
Yes, sir.
somebody told नहीं आ
Yes,
रहा
sir.
है, कोई तो बोला नहीं आ रहा है. ब्रह्मानंद, why do you always try to in mute mode? आप बताओ ना, मैं बोल रहा हूँ आपको.
Yes, sir. I am not in mute mode, sir.
अच्छा, कोई तो बोल रहा था जे समझ में नहीं आ रहा है, फिर म्यूट में चला गया तो. ब्रह्मानंद,
Yes, sir. Yes, sir. I am here, sir.
हाँ
अच्छा, बैकग्राउंड नॉइज आ रहा है इसलिए.
हाँ, कोई तो बोल रहा था ना नहीं समझ में आ रहा है. ब्रह्मानंद,
पता नहीं सर. ये सर पता नहीं कौन बोला.
वेयर आर यू? कहाँ पे हो आप?
लैब में सर.
लैब में कितने
लैब
लोग
में.
हैं?
मैं सर अकेला हूँ सर.
और लैब में ये है गुरप्रीत.
ये सर.
और आप अकेला कैसे हुए? गुरप्रीत को दो, गुरप्रीत को कॉल करो, बुलाओ.
ओके सर.
बुलाओ. ओके करके कहाँ जा रहे हो? वहां से बोलो गुरप्रीत जी आइए.
हेलो.
हाँ
हाँ जी सर,
गुरप्रीत,
नमस्कार.
नमस्कार.
हाँ
वहां
जी,
पे
हाँ जी, नमस्कार
ब्रह्मानंद
जी.
के सिवा और कौन है?
बर्मानंद ही है जी.
और कोई नहीं है?
ना जी ना.
ओके, ठीक है. और सब ठीक है
बढ़िया.
गुरप्रीत? हम्म,
हाँ जी, हाँ जी, हाँ जी.
ठीक है. तो
ठीक है. अब सुनाओ जी.
ब्रह्मानंद, ये सब समझ में आ रहा है आपको?
आइए सर, आप न्यूक्लियर रिएक्शन के बारे में बता रहे थे, जो
हाँ,
बोmbardment
ये
के बारे
समझ
में.
में आया. हाँ, ये समझ में आया.
ये
प्रोजेक्टाइल
सर
कौन
मैं.
है,
ये सर.
टारगेट कौन है, रेसिडुअल न्यूक्लियस कौन है,
टारगेट कौन.
और
ये सर. ये
इजेक्टेड पार्टिकल, ये सब समझ में आया? ओके.
ये सर.
नाउ
ये सर टारगेट प्रोजेक्टाइल रेसिडुअल.
we'll discuss about type of nuclear reaction. We'll discuss types of nuclear reaction. So this nuclear reaction is represented by, as I said, that is X, Y, and Y. Where this is Brahmanand, what is this? Capital X, target nucleus. What is small x? Projectile.
Projectile. Why is the residue?
Very good. Y is residual nucleus. And what is capital I? Sorry, this is capital Y is residue nuclei, and this small y is small y. Brahmanand? Brahmanand?
Uh,
What is it?
ejected.
Ejecting particle.
Eject. Okay.
है ना, जो ऐसे बाहर इजेक्ट होके जाता है, दिस इज इजेक्टिंग पार्टिकल. एंड आफ्टर इजेक्टिंग पार्टिकल इट विल बी ए रेसिडुअल न्यूक्लियाई, और समटाइम्स इट इज कंपाउंड न्यूक्लियाई बोलते हैं, है ना. एंड दिस इज प्रोजेक्टाइल. सो टाइप्स, नाउ विल सी टाइप्स ऑफ न्यूक्लियर रिएक्शन. वन इज इलास्टिक, second is inelastic, third is radiative, fourth is disintegration, fifth is many body reaction. Now we'll discuss elastic. It should be same type, x equal to y, and this will be same. That means here you see, compare these two. Here target nucleus and the residual nucleus is same, and ejected particle as well as projectile is same. So in this case, actually, what is your condition? That means ejected particle y is equal to projectile particle that is x with same energy. Here inelastic, it will be x star. That means this is same, different energy. Different energy, that's why this is excited in excited state. Then it will go, it will emit whatever, that is separate thing, but it will be like this. So in generally in your exam, they ask difference between these, only different energy. Only different energy. Ejected particle and projectiles energy in this case same, where in this case is different. That's why it is in excited state. Radiative capture means क्या होगा? Guess. That means x a radiative capture means Brahmanand, what do you understand? That means क्या होगा?
Sir, it will absorb, I think.
हाँ, very good. Means ये projectile energy को x, projectile particle is small x, absorbed by target nucleus. सपोज एल्यूमिनियम के ऊपर जाके सपोज अल्फा गिर रहा है, वो ऑब्जर्व कर लेगा. After observation, it will get excited. It will form a compound nucleus. Then it emit gamma. It will emit gamma. इसीलिए इसका नाम है रेडिएट. ये रेडिएट करेगा गामा. So this is known as radiative reaction. Is it okay, Brahmanand?
Yes, sir.
That means X absorbed by target nuclei, है ना? Then excited state, then emission of gamma. Is it okay? Then disintegration क्या हो सकता है? A disintegration, this is same type, x, y and capital Y. In this case, सभी का energy, all energies are different from each other. Not energy, all are different. Different either in Z or A or both? Brahmanand, did you understand?
Yes, sir.
Many-body reaction. In many-body reaction, it is like this type of reaction: y1, y2, y3, dot dot dot, y. What does it mean, Brahmanand? Means this projectile incident to X, it is emitting number of particles,
Many ejecting particles.
many ejecting particles. This is known as many-body reaction. That means when energy of X is very high, two or more particles will be ejected. Two or more particles will ejected. That is known as many-body reaction. Now, photodisintegration. First, photodisintegration. What photodisintegration? Whenever target nuclei, ये important for your exam है. Target nuclei bombard with high gamma. It is important. High gamma. Then it will go to excited state and disintegration will occur. So what will be the gamma? Because here what is projectile, Brahmanand?
Gamma, sir.
Gamma. Then Y, capital Y. Okay. Now next is nuclear fission. That you know. Proton incident N or some is coming. So here what will be? When X is heavy nucleus, Y and capital Y both are comparable. Mass and projectile is neutron. In that case, this is fission reaction. Then elementary